Hi there, it's our third look at exercise 20A. That gives you a sign, if nothing else, that there's quite a lot to it. That I'm spending 3 lessons on one exercise. I'm just going to do some more projectile questions, give you a greater variety of questions, I suppose, is my plan here today. A little starter, this should be quite similar. Notice there's no vectors in today's lesson, so this is where they give us an initial velocity. So if you like, here we have to go back to finding ux is 30 cos 40. So I haven't read the question yet, but I'm doing this already. uy is 30 sine 40, whatever those are. So just quickly doing 30 cos 40, and I'm writing 22.98 and 30 sine 40 is 19.28. So I'm sure I'll use it in a bit. So we're firing at a speed. What's the maximum height? Maximum height, remember, occurs when Vy is 0. So I'm going to do suvat, and for part 1 this is, I'm going to do it in the y direction. And I know I want the maximum height. I don't care what the height is. Oh no, I do. What is the maximum height? So I want that. Uy is 19.28. I don't care about how fast it's going then. This is minus 9.8. Oh yes, so Vy is 0, there you go. And that's what I don't care about. So this is S, now V squared equals U squared plus 2AS. So what's that mean? That means that 0 equals that 19.28 squared. 2a is 19.6, so 19.6s, which I should really write as y, I suppose. So 19.6y equals 19.28 squared. If I do that square and divide by 19.6, what do I get? So 19.28 squared divided by 19.6, I get 18.9. Well, 19 meters, 19.0 if I round to 1, throughout 3 significant figures. Now part 2 says, how long does it take for the ball to reach the ground? Again, one thing you need to know, this occurs when it gets back to 0 height again. When it hits there, y is 0. So I can write sy, since I'm in the y direction, I shall write out suvat in the y direction again. And when I do that, that's 0, that's 19.28. How long does it take to fall? I want that, and that's minus 9.8. So that sounds like S equals ut plus a half at squared to me. So my S is 0 equals ut 19.28t minus a half of 9.8 is 4.9t squared. And we've seen a few of these where we take out t as a common factor. We write 19.28 minus 4.9t. And I reckon if I do that 19.28 divided by 4.9, I get the time. I get 3.93ish. It might be a bit of rounding error there, but I reckon t is 3.93 seconds. And then my final question, what's it say? What's the range of the arrow? Well, the range of the arrow occurs when it hits the deck again. Now that happens when x. And we've already seen other examples when the ut plus half at squared, and because we're doing acceleration in the x direction is 0, all this stuff disappears. So it just becomes x equals u. What was u? No idea. 22.98 times by that time we just got, which was 3.93ish. Not an exact answer. Probably should have left an extra decimal place on there. And if in the exam I would have done, I think, times by 22.98. I get 90.4, so I'm not sure how accurate that is. We'll see in a bit, I suppose. 90.4 meters is how far it travels. 90.4 meters is exactly right. Well, there was a slight rounding error there. Other than that, it's all good. Now, horizontal projection. It says a stone is thrown from the top of a cliff. So there's my cliff. It's thrown from the top of a cliff 52 meters above the ground. And it's thrown with an initial speed, it says, 5 meters per second horizontally. This means ux equals 5, but uy has got no component at all. It is thrown initially straight across. the ball obviously will start to drop and it will hit the deck around there somewhere. Modeling a stone as a particle, find the time taken the stone for it to hit the sea. Well, the first thing to note is here, down here, y is minus 52. That's a bit weird. It's fallen. It doesn't go up, it goes down. So y is minus 52. So if I do my suvat in the y direction, this is minus 52. My u in the y direction is 0. Vy is, well, I don't know. Ay is minus 9.8, or it is, and t, I don't know what that is. What do I want the time taken? Now, I've probably got enough information to work out what I got there. So I think that is s equals ut plus a half at squared. Notice I've got uy equals 0 because there was no downward velocity initially. Minus 52 equals u, well, 0 times by t is 0, so I can actually completely ignore that. So half of that, that's minus 4.9 t squared. In actual fact, 4.9 t squared equals 52. If I do 52 divided by 4.9 and then square root the answer, I get 3.26 seconds. That's how long it takes for it to hit the sea. Find the range. Well, the great thing about the range is, as we've seen before, it's x equals ut plus half at squared. But because the acceleration in the x direction is always 0, this thing disappears. X then is just u times by t. Now u, this time, is in the x direction. That's 5. And I can use that 3.26 from the last calculation. So it times that by 5, and I get 16.3. What's that? Meters. There you go. That's the range. They're good. Yeah, they're right. So that was my first question. And this highlights, I suppose, the fact that there are times when you can get the same distance from two different angles. Just be aware of this. So because of trigonometry, the way it works, 15 degrees and 75 degrees as it goes up lands in the same place. You notice 60 and 30 land in the same place. So you've got this rule that if theta compared to 90 minus theta, these two projectiles will land in the same place. If it's 41 degrees or 49 degrees, they will land in the same place. So just be aware of that as a facet of projectiles. Here's an example for us. A ball is thrown with a speed of 14 meters per second from the top of a tower. So that's a u, if you like. A u equals 14. So straight away I'm thinking ux equals uy equals. Does it tell me what the ground is? Oh no, I'm asked to find the angle. So this is all very well, but it's 14 cos theta, and it's 14 sine theta. I don't know much else. 4 seconds later, I'll say from the top of 56 meters above the ground, so that's 56. 4 seconds later it hits the ground, so that takes 4 seconds to do it. So that's t equals 4 seconds. Look, I think I'm going to use suvat in the y direction. Now, the reason why I think I'm going to use the y direction is because I know the s is minus 56. How long does it take for it to hit the deck? Well, that's 56 meters below where it started. Uy is 14 sine theta. Don't care about that one, I don't think I do anyway. This is minus 9.8, and I know it hits 4 seconds later. So I think I can use this as an equation. Let's try it. S equals ut plus a half at squared. So if I put my numbers in, I get minus 56 equals 14 sine theta. That's a bit weird. Times by t, which is 4, plus a half of a, which is minus 4.9 here. We've seen that loads of times. Times by 4 squared, which is 16. So if I just tidy it up a bit, I think I get, for a start, I get 56 sine theta. I'm going to move that thing over there and add it to the minus 56. So what's that give me? It's 4.9 times 16. It becomes a positive. Minus 56 equals 22.4. So sine theta equals 22.4 divided by 56. And I've obviously got to inverse sine it. and I get an angle for theta to be 23.6 degrees. Now, that was actually not so bad. I expected that to be harder. 23.6 degrees. A 10 metre high tree is 60 metres away from a point where the golf ball is hit. The ball just clears 2 seconds after it's hit. Given that the speed is u, okay, this time I want the initial speed. They don't tell me that. Given that the angle of projection is 25 degrees. Okay, so just go through this again. What do we know? Well, we know two pieces of information here, I suppose. So we've got u. Let's do that in both directions. I'm not 100% certain which way I'm going to do it, so I'm going to start with x's. Do I know anything about this? Sx is 60 meters away. Ux is, well, all I can do is u cos 25. And Vx is, what's Vx? I don't care, probably. Ax is 0 and t. The great thing about t is it's the same for both of them. So when I write sy, uy, vy, ay, and t, if I get a result over here, I get the same result over here. So this I know is 10 meters up. It's u sine 25. Vy I don't care about. I don't think I do anyway. This is minus 9.8 and this is t. So I think we've seen before that we can use x equals ut plus a half at squared. But because x has an acceleration of 0, this thing completely disappears. So I get, I suppose, x equals 60 equals u, which is u cos 25 really, times by t. Or put a different way, I can rewrite that as t equals 60 divided by u cos 25. Okay, I like that. So when I come over here, at that same point, the t is also 60 over u cos 25. So if I go through this again, I'm going to use s equals u t plus a half at squared. And my s is 10. My u is u sine 25. And I times it by the t, which I now know is 60, divided by u cos 25. Plus a half of a, which is minus 4.9, times by t, which is 60 over u cos 25. Now this is actually easier than it looks. It wouldn't be if they didn't tell me the angle or the u, but because they gave me the angle, it was doable. Now look, u divided by u cancels out, and sine divided by cos is quite nice. You can work these things out. It's actually tan 25 if you do it. So tan equals, I'm going to just type that in. So the sine divided by the cos times by the 60, I get 27.978. That will do minus 4.9 times, 4.9 times 60 divided by cos 25. That's 324.393 over the u. The u is still there. So I think if I move those over, I'm going to put this, space on the next slide, yes I have. So I'm going to write 324.393 over the u. And notice what I'm doing is I'm moving that over there, and I'm moving the 10 back again, and that 10 will become a minus, so it becomes 17.978. Oops, where's it gone? There. It equals 17.978. And then these two can switch, and my u effectively is 324.393 divided by the 17.978. So 324.393 divided by 17.978 equals, I get 18.04. 18.0, I'm going to say, meters per second. That was my initial velocity. So what does the answer actually say? 18.0, good. Now look, in class then we're going to practice some of these, and I'm going to perhaps have a better look at exactly which questions I want you to do, but there's certainly going to be a range of questions here that are different perhaps from ones we've seen in the past. So we'll have a look at these in class, and they should be a little bit harder. So best of luck.